Welcome to lecture number 45 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done over the last 3 lectures. So, we discussed the stiffness based or displacement based formulation of the nonlinear beam column element, okay. And then we discussed about the flexibility or force based formulation, and then we have studied the numerical integration, how we integrate the section responses to come to the element level, okay, for both displacement based as well as force based formulation, okay. So, today what we will do, we will go through some numerical examples in OpenSeas, okay. So, let us talk about the examples. So, what I will do, I will divide the examples into 3 types: linear elastic behavior, nonlinear response, and within that we will talk about the strain hardening response in this particular lecture, okay. So, let us get started with the linear elastic behavior. So, let us say we have a cantilever column, okay, which is subjected to some axial force P and some horizontal load H. The horizontal displacement I am calling delta H and the vertical displacement I am calling delta V, okay. And this is the cross section is an I section. So, this is the local y, local z axis, this is the local x axis of the element, okay. I will be creating this node first and then this node second, okay. And this is my global x, global y and the rotation theta. The length of the element is L, okay. So, I will be taking L is equal to 3 meter, and for this example, I will be taking NPB 550 by 210 by 92.07. So, we have already used this section earlier when we did the cross section analysis. So, this is coming out of IS 12778 2004. Okay. So, what is the objective? Objective for this example, when we are interested in the linear elastic behavior, is to show that at least 2 Gauss Legendre or 3 Gauss-Lobato integration points per element are required to produce the correct response. That means, the correct stiffness matrix in the basic or deformation coordinates, okay, for linear elastic displacement based elements as well as force based elements, right. And we will also see the effects of number of fibers in kV, okay. So, when we take this cross section, we will discretize it into number of fibers and we will see, if we increase this, what happens, or if you decrease it, what happens, what is the effect on the kV, that is the basic stiffness matrix, okay. For the time being, we will model the cantilever with one displacement based element or one force based element, okay. So, with that, let us look into the OpenSeas example. So, here is the example, okay. So, this import packages is this part is hidden, right. So, I am just using FY 250 MPa, the working unit is kilonewton meter, but I will impose the axial load and lateral displacement in such a manner that the material behavior remains linear elastic, okay. So, modulus of elasticity is 200 GPa, alpha, the strain hardening ratio I have taken 5 into 10 raised to the power minus 3. Again, this and this are not going to be used in this particular example, because we are talking about linear elastic response. The length of the cantilever is 3, and then this H is the depth of the cross section, TW is the thickness of the wave, BF is the width of the flange, TF is the thickness of flange, NFW is the number of fibers in the web, NFF is the number of fibers in each flange. Go back to that lecture where we discussed moment curvature response of this cross section, okay. So, there we have already defined this, right. Then you can calculate what is the area I, the elastic section modulus, the yield moment, the plastic section modulus and so on. I am also printing the EI value, which is this much kilonewton meter square, okay. And as you can see, Py, the yield axial force is A into Fy, I am applying only 5% of Py. So, very small load, so that it remains linear elastic, okay. And then we create the model. So, this is 2 dimension, per node we have 3 degrees of freedom, because we are dealing with beam column element, okay. So, this is node 1 at 0 0, node 2 is at 0 and L, okay. So, create the nodes, then the bottom node is fixed, and here I am using steel 01 material, which is bilinear plastic. So, material tag 1, Fy, E and alpha, and then again this was done earlier. So, we are doing the section discretization using the WF section 2D command. So, this is the section tag, steel material tag, H, TW, BF, TF, NFW and NFF. If you give this, it will do the discretization. So, how many fibers we are taking? We are taking 20 fibers in the web and 5 fibers in each flange. Okay. So, the element geometric transformation remains linear. Integration tag, I am saying this is, let us say 1. Number of integration point, right now I am using 3. Okay. So, let me go back to integration point 2, and then here let me keep it Lobato. So, 2 integration point with Lobato, and then I am first looking at displacement beam column element. The command is dis beam column. This is element number connecting node 1 and 2. Node 1 is ith node, 2 is jth node. Transformation tag is linear, there is no p delta. Integration tag is this one where we are defining the Lobato integration. Okay. This is the model. Let me run it. Now, let us first check the stiffness matrix. So, from OpenSys you can get the basic stiffness matrix, basic stiffness within bracket the element number which is 1 here. Okay. Now, what I am doing, I am actually doing all this to print it in this manner. Okay. So, this is the OpenSys basic stiffness matrix. If you go back to the lecture on displacement based element or on force based element, and even if you go back to direct stiffness method approach, which we started at the beginning of this semester, okay, you will see that Kv is A by L 0 0 0 4ei by L 2ei by L 0 2ei by L and 4ei by L. So, I am printing that one as well. Okay. Now, you see that this number and this number is matching well. Okay. But what about this? This versus that number are not matching quite well, because if you remember in the previous lecture, I theoretically proved that you need at least 3 Gauss-Lobato integration points to be able to accurately integrate the section response for linear elastic system, or to get exact response for linear elastic behavior, you need at least 3 Gauss-Lobato integration points. So, intentionally I kept it 2. So, let me go back and make it 3 and rerun this. So, make it 3. And now you see this is 1.514 10 raised to the power 5, and this is again 1.515 10 raised to the power 5. You compare these numbers, they are pretty much very close to each other, right. So, not much error. Now, if you change the fiber section discretization, if you use less number of fibers, then what will happen? These 4 numbers may not match quite well with the exact solution, because your eye, to be able to capture the moment of inertia accurately, you have to discretize the cross section in many fibers. Okay. So, now with that, let us keep going. So, I am now applying a linear time series, okay, to apply the gravity load, right. So, pattern time series linear, time series tag is 1, then pattern plane pattern tag time series tag, and at node 2 in the y direction, negative y direction, that is vertically downward, I am applying P load, which is 5% of the cross sectional yield strength. Okay. And then this is the analysis configuration, which we have used many times. So, I am saying in 5 steps, n steps g for gravity, apply the gravity load. So, my increment, the load factor is 1 divided by n step g, and the analysis is static. And then for lateral load, I am saying we will apply the lateral displacement, okay, in 10 steps. So, my total step is n step gravity plus n step lateral. Okay. And then this is delta is an array where I am storing the displacement of the top node, okay, and RF is an array where I am storing the reaction force at the base, and then this basic force, basic deformation also you can record, section force, section deformation also you can record. We are not going to use the basic and section forces in this example. Okay. So, now for n step g, we perform the analysis, okay, and record the delta. So, this first entry is the horizontal tip displacement of the cantilever, second entry is the vertical tip displacement, that is how I have stored it. Okay. And this is the horizontal reaction first entry, vertical reaction is the second entry, and you can also save the basic forces. Okay. Then you put load constant time 0, this is very, very important to keep the load constant and reset the time. Okay. So, then we are applying the lateral load. So, we have to apply reference load unity in the x direction at node 2. Okay. And then I am saying the total displacement I want to apply is only 0.1% of the height of the cantilever, very small. Okay. And that I will be dividing into n step lateral, which is 10. Okay. You can see n step L is 10. Okay. Then I am doing the displacement control analysis. So, this is where we run the loop to apply all the displacement and then again record the delta and the reaction force. Okay. So, now let us go to the results. So, moving forward, we will be talking about global response and local response. So, in this case global response is important. So, global response means I am interested in this P versus delta V and H versus delta H relationship. So, that is the global response. Okay. So, if you look at it, the red with dot is the OpenSys solution for axial force and vertical displacement. So, that means this is P versus delta V. Okay. And the green one is the exact solution. Because the response is linear elastic, I know what is the relationship, right? Delta is equal to PL by AE. Similarly, on the right hand side, lateral force versus displacement, you can see the red is the OpenSys and green is the exact solution using Euler-Bernoulli beam theory. Okay. And they are matching exactly well. So, what I have done? I have used 3 Gauss-Lobato integration points. Okay. I discussed this. That is this analysis case Gauss-Lobato with 3 integration points. Okay. Now, let me go back and change it to Gauss-Legendry. I have discussed that, or I have shown you theoretically that only 2 Gauss-Legendry integration points are good enough to get the exact solution for linear elastic behavior. So, therefore, I changed it to 2 and beam integration legendary, again displacement based element. So, let me run it and you can compare, this file is shared with you, you can compare the KV, again they will match quite well. Okay. And then finally, if you come back and look at the response, the global force displacement response, okay, let it complete. So, again you see that it is matching extremely well. Okay. So, this is with 2 Gauss-Legendry integration points, right, with displacement based element, right. So, if we change the number of integration points, we cannot use one integration point, but we can certainly increase, but that is not necessary as long as the behavior is linear elastic. So, let us say if I make it 3, then go to the global response, okay, there is no change, right, because to get exact solution for linear elastic behavior, you need only 2 Gauss-Legendry. Okay. So, this is done. So, what we have concluded that minimum 2 Gauss-Legendry IP and 3 Gauss-Lobato IPs are required for linear elastic response using displacement based element, and one displacement based element is good enough for linear elastic response. As you can see that the axial force displacement and lateral force displacement are matching quite well with the exact solution. The green is the exact solution. Okay. Now, remember that a minimum number of fibers are required for the cross section discretization, and this should be established using a convergence study at the section level. Please go to lecture number 24 where I discuss this. Okay. You have to look at moment versus curvature convergence. Okay. I will show you quickly what happens. So, let me go back and change the number of fibers. Okay. So, I have used 20 instead of 20, let us say I use 5 fibers here and 2 fibers here. So, in the wave I am using 5, in the flange I am using 2, and let me change the number of integration points to 2, and this is still beam legendary and displacement beam column. Okay. So what I will do, I'll quickly show you the effect on this. So what is the effect? You can see this is 1.504 and this is 1.515. There is a slight difference in calculation of the moment of inertia. Okay. And is there any effect on the global response? Well, you can see now some departure, right? If you reduce the number of fibers in the cross section even further, then this will increase, the error will increase. Okay. Now, the next thing I want to do is the same exercise, but for force based element. First, let's go ahead and do it for, this was Gauss legendary, okay, earlier. So, Gauss legendary, and then instead of displacement beam column, I'll now make it force beam column and change the section to what I had 20 and let's say 5, okay. And if you go back to the global response, you can see you get exact solution. Again, if you change the integration points, let me make it 2 and change it to Lobato, okay, and show you what happens. So, force beam column with Lobato, but 2 integration points. So, let us see the global response. You see this is exact versus that is open seas. So, you are not able to capture the response accurately, because as I said earlier, you need at least 3 Lobato integration points, okay. And now we will see that they are matching quite well, okay. So, this is done, Gauss Lobato, Gauss legendary done, okay. And again minimum 2 integration points for Gauss legendary, 3 integration points for Gauss Lobato are required for linear elastic response. And for linear elastic response, 1 element is good enough, okay. So, that was kind of a trivial case. Now, let us go ahead and study nonlinear response, okay. Before I begin, let us recall the differences or the similarities between the two, okay. So, the differences are displacement based beam column element is based on displacement interpolation function Ax, which is basically a matrix of shape function. On the other hand, force based elements are based on exact force interpolation function Bx. Just go back and revisit the previous lecture, okay. So, displacement based element requires finite discretization for members that are undergoing inelastic deformation or regions where you have inelastic deformation. So, there you have to do a finite discretization. I will show all of this through example. Whereas, for force based element, only one force based element is sufficient for yielding member, okay. For the displacement based element, accuracy cannot be improved by increasing the number of integration points beyond a minimum, whereas for force based element you need only one element per member and you have to increase the number of integration points for yielding members and get a converged solution, okay. For strain softening behavior, localization of response happens over one element. Here for force based element, localization happens over one integration points. So, all that I have stated here will be proven slowly as we go along, okay. Let us understand what is strain softening response and what is strain hardening response. So, strain hardening response is typically observed in steel members if the local and lateral torsional buckling are prevented. If there are no instability, okay, then you can get, let us say for this cantilever, the horizontal load versus delta relationship is initially linear and then there is this hardening. So, this is called strain hardening response. On the other hand, strain softening response, which is typically observed in reinforced concrete members, especially subjected to large gravity load, okay, the lateral force versus delta relationship increases, goes to the peak and then it drops down, okay. So, this is called strain softening. What is in between? Well, the in between what we have is elastic perfectly plastic behavior, EPP, okay. So, let us first study examples of strain hardening response, okay. Softening is more complicated, we will get there, okay. But before that, let us first talk about strain hardening examples. So, again I take the same cantilever with gravity load P, horizontal load H, which will apply through a displacement control mode, and now the material sigma epsilon response is like this, which has an alpha, the strain hardening ratio. I already had it, but did not use it. So, alpha is 0.005, Fy is 250, and section discretization is same as lecture number 24. Okay. Now, what is the objective? The objective is to show that increasing the number of integration points cannot produce an accurate solution in displacement based element. On the other hand, increasing the number of IPs produces an accurate response in force based elements. Okay? That is the objective I want to show, what that I already claimed in the previous slide. Okay? So, how do we do that? We will look at two different types of response quantities. One is global and the other one is local. For the global response, we will look at lateral force H versus lateral displacement delta H and vertical force P versus vertical displacement delta V. For the local response, what we will do, we will look at the variation of section forces. So, integration points means what? Section. So, for example, if we use Lobato, we have a section or an integration point at the two ends of the element, and then we have, if you are using 3, so you have 1 here, depending on how many integration points you are using. So, you will have this sections, right. So, we will look at the axial force and bending moment at different sections along the length of the element, and then we will also study the variation of section deformation, that is axial strain and curvature at different sections along the length of the element. We will also study the force deformation response, that means moment versus curvature at the base and axial force versus axial strain at the base, because this is a cantilever which is going to deflect like that, and the plastic hinge is going to form here, where the plasticity will distribute. Okay. So, because we have maximum moment at the end of the element where the plasticity will be more pronounced, we would like to consider that section in our integration. And if you go back to the previous lecture, you will see Gauss-Lobato has integration points at the element ends, whereas Gauss-Legendre doesn't have any integration point at the element ends, it has somewhere in between. So, therefore, we will be using Gauss-Lobato integration points for this study. So, let me go to the example, the same cantilever. Okay, I am not going to go through all this again, because this is same as example number 1. Okay. Now, here I am saying 3 integration points, Gauss-Lobato, and using displacement beam column element, right. And let me go to the results directly. So, the global response is, the red one is the computed response with 3 integration points with displacement based element, and the green one is a reference solution which I am claiming exact solution, or at least tending to the exact solution, obtained using 16 number of force based element with 5 integration points per element. So, it is a very finer discretization and using force based element. So, now let us look at the comparison. So, you see the lateral force versus lateral displacement response does not match well. Okay. Now, if you look at the variation of the curvature, so I am looking at curvature at this section. So, I am using 3-point Gauss-Lobato. So, there are 3 integration point, one at this end of the element, other is at that end. So, this is my length of the element 0 to 3 meter, okay, and one is at the middle, right. So, this is the variation of curvature along the length of the member, whereas the exact curvature variation is like this. Okay. So, here you are getting the inelastic deformation, hence the curvature is increasing significantly. Okay. The moment diagram, if I look at, so this moment diagram is constructed by plotting the bending moment at each section. Okay. So, we have 3 integration point, meaning the 3 section. So, here, here and here, and as you can see, we have a cantilever which is post bilateral displacement. I expect a linear bending moment diagram, but that is not happening. Okay. Because the assumption of displacement based element is that the curvature varies linearly, which is what you can see, the curvature is varying linearly. So, therefore, the global response does not match. So, you can play with this. So, for example, if I change this time, the step number, and take it to when it is linear elastic, then you can see that the exact solution and computed response are matching well. You move it slightly, then also it is fine. But the moment you get into the nonlinear response, then you see that the differences are large. Okay. Similarly, this is for axial force variation along the length. Now what you notice that I have applied some axial force to this cantilever, but at this section the axial force is some value, here it is some other value, here it is some other value. Okay? Why? Because if you recall, in displacement based element, the equilibrium is satisfied in an integration sense. So, it is a manifestation of weak equilibrium. Okay? Again the same response I am showing here, but if you go to elastic conditions, things will, so you can see then the match is quite well. Okay? That is I have already shown that earlier. Okay? Now, you can also look at the moment curvature response and axial force versus axial strain response at the base of the cantilever. So, I have this cantilever. Okay. So, I am looking at the axial force, axial strain here and moment versus curvature at that location. Okay. Again, you can see that it is far from the exact solution. Now, let me increase the number of integration point and show it to you. So, instead of 3, let me go directly to 7 integration points and run the analysis. So, you can see neither the global response, the lateral force displacement, nor the local response are matching with the exact solution. Okay? Because in displacement based element, because of this assumption that the curvature varies linearly, you will not get exact solution. Okay? So, and you can see if you integrate this axial force, meaning that, so this is basically you add all of them and average them, it will match with the exact solution. Okay? So, this is what I am also showing here for 7 number of integration points, these results are not matching. So, 1 dB cannot produce an accurate solution no matter how many integration points are used. Okay? Now, let us talk about force based element, right. So, in the same example, what I will do, I will go here and first use 3 and change this to force beam column. Okay. I have one element, right. So, let me go to the global response and see what happens. Well, it is far from the exact solution, but we will see what happens if we increase the number of integration points. Now, let us look at the bending moment. Remember, in the force based element, we actually use a force interpolation function, right. So, therefore, the bending moment distribution which we expect to be linear is exactly linear, that is the red, but it does not match with the correct solution because we have less number of integration points, and see the curvature variation also does not match. Okay. Similarly, you can look at the other response quantities, they are not matching well. Okay. So, now let me do one thing, let me increase the number of integration points. So, make it directly 7 and now look at the global response, reference versus computed are matching quite well. Okay. One element, 7 integration points. Okay. Look at the curvature distribution. So, these are the integration points where I am recording the curvature, and you can see they are all on top of the reference solution. The bending moment diagram is again matching with the reference solution. You take it to the end of the simulation, that means at this point, then also it is matching. Similarly, for the axial force, the axial strain variation along the length of the element, they are matching quite well, because in the force based element we are not making any assumption about the distribution of the curvature or the axial strain, unlike the displacement based element. Okay. You can also look at the section moment versus curvature response at the base of the cantilever. So, it is matching quite well. Okay. So, from here, so this you have already seen, one FBE can produce an accurate solution when you have enough number of integration points for strain hardening type of response. Okay. So, now again take the same example, but I want to show all the results together. So, I am not going to open Cs, but that example is already shared with you. So, what I am doing, I am plotting the axial force versus vertical displacement for the cantilever, and 3, 5, 7, 9. These are increasing number of integration points I have used. Okay. And you can see that the results are converging. Here the maximum vertical displacement tends to converge. So, red is for 3, then green, blue, black, they are basically converging. On the other hand, lateral force versus lateral displacement, you can see the solution has converged, okay, with even 7 integration points. Look at the variation of the curvature along the length of the element, okay, and the bending moment. You can see with increasing number of integration points how the bending moment variation, the curvature variation along the length is actually converging, right. So, both global and local response, local means the response at the cross section level or the integration point, are actually converging, right. So, for all the details you can go to this example which is already shared. So, example number 3. Okay. So, with that let me summarize. So, what we have done in this lecture, we have looked at a linear elastic response and we have demonstrated that you need at least 2 Gauss-Legendre integration points or 3 Gauss-Lobato integration points for linear elastic response, be it a displacement based element or a force based element. Okay. Then we have discussed what is strain hardening versus strain softening response. For strain hardening type of nonlinear response, we have studied one example, and from that we concluded that one force based element with sufficient number of integration points can capture the nonlinear response, both the global as well as the local response accurately. Okay. And we have discussed that, or we have demonstrated that one displacement based element, no matter how many integration point you use, is not sufficient. Okay. So, what you have to do? You have to increase the number of displacement based element. You have to do a finer discretization, a finer mesh. Okay. Then only you will get an accurate solution. Okay. So, that means you will have to increase the number of degrees of freedom, or that will increase the number of degrees of freedom of your model. So, which is not very computationally cheap. Okay. In the next lecture, we will talk about the convergence of response if we increase the number of displacement based element, and then we will talk about the issues with this type of element formulation, okay, that is called localization. Okay. So, with that, thank you and see you in the next lecture.